Hi, so in this video we're going to be looking at balanced growth paths in the Solow Growth Model. So initially just discussing what balanced growth paths are and then showing what the actual balanced growth path in the Solow model is. So what is a balanced growth path, or a BGP for short? Well, this is an equilibrium of the Solow model where we have capital, output, consumption, wages, and the return to capital all growing at a constant rate. So we can think of, and I'll use this notation as the growth rate of capital and the growth rate of output and so on, the growth rate of consumption. And so we're not talking about when these values themselves are constant, we're thinking about their growth rates all being constant simultaneously. And we care about balanced growth rates because this is seen to roughly be the case in a number of developed economies. We'd say, for example, see that our output tends to grow at, say, 2%, and this is a target that lots of developed economies aim for, or 2.5%, or whatever it is, and we sort of think that this is a fair enough representation of what developed economies tend to look like. So we can show that the Solow model has a balanced growth path by just working through the Solow model and just looking at the growth rates, and sort of by assuming that these growth rates are constant, we can find out what the actual growth rates of them will be when they are constant. So as with many things in the Solow model, we're going to start with the capital accumulation equation. Here we've assumed that we have this neoclassical production function where we have y is equal to, say, k alpha multiplied by al to the 1 minus alpha. This is maybe slightly different to a Cobb-Douglas technology where we have now the a inside the bracket, so we have a to the power of 1 minus alpha. This is just choice, really. It's still a neoclassical production function, but we now are thinking more of effective units of labour, which we call AL, than just units of labour L. So it's fine, we can just use this for the purposes here because it makes things a little bit simpler to work through when we think about balanced growth paths. So our Solow capital accumulation equation is given here. The change in the rate of capital is equal to our investment minus our depreciation. We've covered all of this in previous videos, so check those out for getting to this stage of the Solow growth model. And as I say, we're looking at growth rates of capital, so we're going to be looking to find what the growth rate of capital is in our Solow accumulation equation. And we are going to need to know our growth rate rules for this part of the course. I'll try to give some hints at when we're using each specific growth rate rule in this video, but we can define our growth rate is equal to k dot over k, and k dot of course is the derivative of this variable with respect to time, and so k is going to grow over time, and that's equal to k dot over k. So we can just divide through our capital accumulation equation by k, and we get this right hand side of the equation, just simply dividing through by k, and we'll notice that the powers on these k term and the al term are such that we can put al over k to the power of 1 minus alpha. So now we're going to be looking for the balanced growth path, and one thing that we need to notice is that what we've said on a balanced growth path is that this gk term has got to be constant. We're looking for when the growth rate of capital is constant, and when this is the case, we're going to need, because we've said that gk is equal to this expression here, we're going to need that this expression is also constant, which we know that this depreciation term is just some constant parameter that we choose. This savings parameter again is just constant, and this 1 minus alpha is constant. So for gk to be constant, we're going to also need that al over k is constant. And what does it mean for something to be constant? Well, it means that the growth rate of that variable is equal to 0, and that's just what I've written down here. We're going to need that the growth rate of al over k is equal to 0. And for al over k to be constant, it's sufficient for the top of the numerator, or should I just say the numerator, to grow at the same rate as the denominator. So we have AL over K. If AL at the top grows at some rate, so the growth rate of AL is equal to, let's say, just 5, just some random number, and the growth rate of the denominator is also equal to 5, well, these are just going to cancel out, and because the top and bottom are growing at the same rate, so the overall growth rate is still going to be 0. And so that's what we've done here. And we could also just do this through rules of logarithms, or growth rate rules, because we effectively think of these growth rates as natural logarithms. We could just write this as GL minus K is equal to 0, because we have AL over K, and in logarithms, AL over K, or the natural log of AL over K, is just the same as the natural log of AL minus the natural log of K. But okay, this should be fairly straightforward. And again, using rules of logarithms, we know that ln of AL is equal to ln of A plus ln of L. So we can split the growth rate of AL into GA plus GL. This is still equal to GK. And we've defined in the previous set of videos that our growth rate of technology is equal to G, and our growth rate of the population L is equal to N. So now we found what our growth rate of capital is. Our growth rate of capital is G plus N, just by working through the fact that we've assumed that we're on a balanced growth path, and if we are on a balanced growth path, our growth rate of capital has got to be G plus N. So on a BGP, capital grows at G plus N, and that is constant. Okay, so now that we've got that, it is also worth noting that if the growth rate of AL over K is equal to 0, we have that 1 minus alpha is a constant, so the growth rate of AL over K to the power of 1 minus alpha is also going to be 0, and we can use this result later on, or right away, as it turns out. So remember that we defined our production function to be AL to the power 1 minus alpha multiplied by K to the alpha, and we can divide through by K to get Y over K. Why we do this will be clear in just a second, but if we divide through by K, we will notice that this K goes to the alpha minus 1, and then we can just write this term like so. Y over K is equal to AL over K all to the power of 1 minus alpha. And then what we'll notice, as we've just written down here, we will see that Y over K is thus growing at this A over K, or AL over K to the 1 minus alpha. If we were to take growth rates of both sides, we would see that Y over K is growing at the same rate as 1 minus alpha, which is the same as growing at AL over K, which is equal to 0. And as we did just before, we can say that gy over K is equal to 0, as we've just found. Well, this means that gy minus gk, using rules of logarithms, is equal to 0, so gy is equal to gk. So in a balanced growth path, a very nice result is that the growth rate of output is going to be the same as the growth rate of capital. And even further than that, since in our Solow model we've assumed a constant savings rate S, so everybody saves a certain fraction of their income, we can write down this result that consumption is just some fraction of savings, because we know that output is split between consumption and investment. So we have that our amount of investment is equal to the savings rate multiplied by the output. So our consumption is equal to anything left from this 1 minus S multiplied by Y. So then we can just take the logarithms and take the growth rate rules of both of these sides of the equation and see that the growth rate of consumption is going to have to equal the growth rate of 1 minus S multiplied by output. And as we've done before, this means that the growth rate of consumption is equal to the growth rate of 1 minus S plus the growth rate of Y but 1 minus s is a constant. We have a constant savings rate, so this is just going to be equal to 0. And so our growth rate of consumption is equal to the growth rate of output, which, as we said above, is equal to the growth rate of capital. So all of these key variables grow at the same rate, which is very nice. We just need to remember that these all grow, and as we found the growth rate of capital, these all grow at g plus n. Now, I did say that in a balanced growth path, we also have the wage rate and the return to capital growing at the same rate. They're maybe not as important. We don't necessarily, we don't necessarily care as much about the wage rate and the return to capital. We do care about how our output and our consumption grow, but it is worth noting what these wage rates and return to capital actually grow at. So how do we get this equation here? I just written down what the wage rate is in terms of our capital, labour and technology. Well, we know this because we had our production function, k to the alpha, al 1 minus alpha, and we derived this in previous videos where we have the firm's profit maximization problem, where they're maximizing profits, which was k alpha, so they maximize their output minus the wages they have to pay minus the rental rate of capital multiplied by the capital stock. And we can take the first order condition with respect to L, and if we work through all of that, we see that we'll get out this equation for the wage rate. If we take the first order condition with respect to L, we get just W here is equal to the derivative of output with respect to L, and this is, well, these two terms are equal to 0, and then we can rearrange appropriately, and we get that the wage rate is equal to this, where our wage is equal to the marginal product of labour. And so we can rewrite this by just moving the a into the bracket so that we get this k over al term in brackets, and we know that this grows at a constant rate, so we're doing something very similar again. We're rearranging to get k over al, and so we can take growth rate rules. So the growth rate of w is equal to, well, we know that rules of logarithms, these two are multiplied together, so when we take logarithms, we can just add them together. So the growth rate of k over al to the alpha plus the growth rate of a, and we know that k over al grows at a growth rate of 0. So this is equal to 0, and so our wage rate just grows at our rate of technological progress, g. G, of course, is equal to GA here. We just defined it to be, we just called it G. So our wage rate doesn't grow at m plus g like the other things do, but it grows at rate g, so still very, very simple to remember. And then finally, we want to look at the constant growth rate on balanced growth path of the rental rate of capital, RK. And so this initial equation, where did we get this from? Well, similarly, we have the firm's first order condition, but we differentiated profits with respect to capital. So I won't go through all of that, and actually we've got an alpha here, so maybe above we needed to have a 1 minus alpha, but it would have cancelled out because these are just constants. They don't matter too much because their growth rate is 0. So we would get rid of them anyway. But let's look at what the growth rate of the return to capital is. Well, if we take a growth rate of this, I've basically just taken the growth rate, and we can split this up into g alpha plus g al over k 1 minus alpha. We can do whatever we can split it up as many times as we want. What we're going to notice is that this is constant, and this al over k is constant, as we said before. It's not necessarily constant at all times, it's worth noting, but on a balanced growth path, we have to assume that al over k is constant for the reasons I mentioned at the start of this video. So the growth rate of the rate of return of capital is 0. So we had that our variables, y, k, and consumption, they grow at n plus g in balanced growth path. We had the wage rate was growing at g, and we had that our k is growing at 0. So that's our balanced growth path in the Solow growth model. What we'll be doing in the next video is looking at convergence to the balanced growth path. So make sure to check out the playlist for that next video. Make sure to leave a like if this video was at all useful, and do subscribe for lots of future economics videos.